Hi, this is John, and this is lecture 3 for week 5 of CS 1030. What we're going to do today is we're going to look at how to find the value of a binary number. That is to say, a number written down or stored in the binary representation, which is the same thing as saying a number written in base 2. So let's just keep in mind that numbers have no base abstractly. They're just numbers. They get a base when we write them down or store them in a computer or something like that. And something we often need to do is take a stored number in base 2 or base 10 or base whatever and figure out what number it actually represents, what the abstract value represented by that number is. So we're going to look at an algorithm. And so let's sort of go through this. So we want to find the value stored in a base 2 number. The input to the algorithm is going to be a number. We're going to call it num. It's in base 2, and it has the digits, and they're binary digits, D0 through Dn. And the way this is going to work is D0 is going to denote the least significant bit of the binary number, and Dn is going to be the most significant bit. And so then we can use this notation to sort of look at the individual bits in the number, and we're going to use that as one of the mechanisms for finding its value. So to initialize the algorithm, we have two state variables. We set pos, that's a position state variable, to 0. That means we're going to be starting at position 0 in the binary number. We're going to be looking first at its least significant bit, and pos is going to end up counting up to n. And sum is the current, so sum is going to sum up the contributions of the various bits to the number that's represented. And it starts off at 0, and it ends up holding the correct value. And in the middle, it's going to hold something which is an intermediate value, which is going to be just the sum of the digits we've summed up so far. Okay, so let's see how this works. So we have a while loop. So while pos is less than a number of digits, so pos is going to start at 0 and go to the number of digits, we are going to increase sum by the value of the digit at position pos multiplied by 2 to the power of pos. Okay, so we'll see how that, let's just sort of leave that here for now. We'll see how it plays out in a minute. So let's just sort of, hopefully this isn't confusing. It's something that's really easy going on here, but this is sort of the easiest way to write it down. And then we increment pos. After we've incremented the value of pos to pos plus 1, we go back to the start of the while loop. And when this while loop finishes, then we are going to output sum, and it's only at the end that sum is going to contain the actual number represented by the binary number. So, okay, so let's go through this algorithm. So we just want to sort of keep track of everything that's going on here. It's a little bit more involved numerically or mathematically of an algorithm than we've seen before. It's probably not more complicated than algorithms that we've seen, like some of the sorts, but there's a little bit more to keep track of. So what we're going to do here is find the value of 101 written in base 2. So the binary number 101. The question is, what is the number represented by it? Okay, so initially in the pos is going to be 0 and sum is going to be 0. That's the setup for the algorithm that we saw on the previous slide. And now in the first iteration of the while loop, pos is going to be 0 because we haven't incremented it. The digit stored at pos in the binary number is 1. And that's because position 0 of the binary number contains 1. 2 to the pos, 2 to the value of pos is just 1. So the way to say that is 2 to the 0 is 1. Any number, in fact, to the 0th power is 1. And now if we multiply the value of the digit at pos, so that's 1, times the exponent, we just get 1 times 1 is 1. And that is a value that we add to the state variable sum, which previously contained 0, so now it contains 1. And all this is really saying is that the binary number, the binary digit 1 stored at the least significant bit contributed a value of 1 to the value of the binary number. Okay, in the second iteration of the while loop, pos is going to have been incremented to 1. The value of the binary number at pos is 0, so you can see that position 1 of the binary number contains the binary digit 0. 2 to the pos, so 2 to the 1 means we just have 1, 2. It's just 2. We don't multiply it by anything, so that contributes a value of 2. And we multiply 0 times 2, and we get 0. So the 0 in the second position up from the least significant bit contributes nothing to the value. And that's should be what you expected, I hope. In a binary number, or a decimal number, or a number in any base, zeros are just placeholders. They're used to put other numbers in the correct positions, and they never contribute anything to the value of the final number. Another way to think about that is you can imagine that numbers have lots of leading zeros, and those never contribute anything either. Okay, So in the third iteration of the while loop, pos is now 2 because it's been incremented from 1. The digit stored at position 2 here is going to be 1. 2 to the pos is 2 to the 2, which is just 2 times 2 or 4. And so 1 times 4 gives us a value of 4. So a 1 in this bit position contributes a value of 4 to the overall binary number. So we add 4 to what was stored in the variable sum, getting 5. And now we're done with the algorithm because now that pos goes to 3, we can see that it refers to a number that's refers to a position that's outside of our stored binary number. So that's the termination condition for our algorithm. And so the final integer represented by 101 in base 2 is going to be the number 5. Okay, so hopefully that was fairly clear. We're going to sort of look at a bunch of sort of similar stuff like this, but it's important that you understand this. So if you didn't, either ask us a question or in recitation or online, or watch the video again or something, because this is important stuff. So if you look what's really going on here, the value of a binary number is basically just the nth bit position, the digit at the nth bit position times 2 to the n plus d to the value at the n minus first bit position, so the second bit down from the most significant bit, times 2 to the n minus 1. And that pattern continues all the way down to the digit at bit position 1 times 2 to the 1 plus the digit at bit position 0 times 2 to the 0. So this works for any binary number, and it lets us recover the actual number that's represented. So if we wanted to do this in Scratch, for example, why did I show you a while loop? Why not just write down this formula? Why not just sort of create a sequence of Scratch blocks that does this computation? And the idea here is that if we don't know in advance how big of a number we might be dealing with, then writing out this formula really isn't going to work, because we might get a number that's bigger than the number of terms of the formula that we've expanded out. So if we have a loop, it'll work for any number. And so it's just a better representation for this particular algorithm, a better way to think about the algorithm. And so let's end up by talking about something, which is that how would we change that algorithm to find the value of a number in a different base that's other than base 2? And I'm not going to answer that right now. I would like you to think about it. And if you can come up with the answer, that's great. If you can't come up with the answer, then I would like you to ask about it during recitation this week. Thank you.